In this lecture, I want to introduce reverse mode automatic differentiation. The Julia library Zygote does automatic differentiation. If we were doing our large-scale machine learning projects in Julia, you would be using the Flux deep learning library, which is implemented on top of Zygote. So what does Zygote do? Well, among other things, it can automatically compute the gradient of a function. So the Zygote library provides us a gradient function that takes in another function and arguments at which to evaluate the gradient, and it tells us that at the input point 1, 2, minus 1, the gradient of this function is 22, 4, minus 12. And we could verify that by taking the symbolic derivative of this function and plugging in the point 1, 2, minus 1. So that's handy, but so far not very different from what you implemented way back in Project Zero. What's awesome about automatic differentiation is that it allows us to compute gradients of much more interesting functions. So let's consider a function that you've probably implemented at some point in your past computer science career. So this function lets us compute the nth place in the Fibonacci sequence. So we can compute fib of 0, 1, 12, and that will give us that the 12th element of the Fibonacci sequence is 144. But this version of the function also lets us specify other starting points besides 0 and 1. And now, with the gradient function from Zygote, we can compute the gradient of this Fibonacci function. And it tells us that at the inputs 0, 1, and 12, the partial derivative of the function with respect to a is 89, the partial derivative with respect to b is 144, and there is no partial derivative with respect to n. This makes sense because the variable n is not a continuous variable in this function. It's used only as the loop constant, and so if we made a small perturbation to n, we wouldn't have any change in the output of the function. But it's saying that if we made a small perturbation to a, that would have an 89 times larger effect on the output of fib. And we can test that numerically. So let's set an epsilon to some small value, and then we can compute fib on 0, 1, 12, and compare that to fib computed on epsilon, comma 1, comma 12, and then divide that by epsilon, and we get approximately 89. Similarly, for the partial derivative with respect to b, we could take a finite difference at 1 to 1 plus epsilon and get approximately 144. So how on earth are we computing the gradient of this complicated function with a for loop? It turns out there are several ways that this can be done, and they fall into a few broad categories. The category we're going to focus on is reverse mode automatic differentiation. And the way reverse mode automatic differentiation works is to essentially build up a computation graph automatically as the function is being executed, and then to backpropagate partial derivatives through that computation graph. So let's switch over to the iPad and draw this out. If we want to compute the partial derivative of a function like fib with respect to its inputs a and b, The key idea is to replace those variables, a and b, which are currently just holding numerical values, with objects that can hold both the numerical value and some additional information that helps us in computing derivatives. There are two types of information that we could store in these variables. The first, for forward mode automatic differentiation, would store both the value of the variable and the partial derivative of that variable's value with respect to each of the inputs to the function. The second version, for reverse mode automatic differentiation, would store, along with the value of the variable, the other variables that preceded it in the computation, and the function that was used to compute its value from those predecessor variables. For this example, it would be pretty feasible to do forward mode automatic differentiation by hand, and I will post a reading by Dr. Neidinger on how that works. But for deep learning, reverse mode automatic differentiation is much more useful. The basic reason for this is that forward mode scales in the number of inputs because we have to propagate a partial derivative with respect to each input, and in deep learning we have an enormous number of inputs, namely all of the weight parameters in the network, and so forward mode would get out of hand quickly, whereas reverse mode scales in the number of outputs, which is typically 1, just the network's loss. So the purpose of these reverse mode autodiff objects is to automatically construct a computation graph while evaluating the function that allows us to later backpropagate the derivatives. We start with two of these objects corresponding to the two inputs to the function with respect to which we want to compute partial derivatives, and they have a value equal to the values that we passed into the function, and they have no prior values and no function that was used to compute them, so those other fields will be null. And now, as we proceed through the function, at every step we want to create a new variable storing the intermediate result of that computation. On the first iteration of this for loop, when I equals 2, we'll get intermediate values that we can call C2, B2, and A2. And so C gets the value 1, and its value depends on inputs A and B, and we get that by the function plus that adds A to B. Whereas B2 and A2 get their values from assignment statements from a single previous variable. On the next iteration of the for loop, we'll get intermediate values C3, B3, and A3. C3 will get the value 2 from inputs A and B, and we add them together. B3 gets its input from C3, and A3 gets its input from the variable B2. And we can proceed forward like this until we get to the end of computing the function's output. By keeping track of all of these intermediate variables along the way, we have been implicitly building up a computational graph, where these parents in the object tell us which other nodes in the graph feed into the node for this variable. And so we can draw in all of those dependencies and also the function nodes that produce the value of a variable. And once we have added all of these parent edges to the graph, we have what is essentially a complete computational graph for this function. Along the way, we stored the value of each of the intermediate variables, and so when we get to the end, we know the output of the function. And so we can use the computational graph and the intermediate variables to perform backpropagation. Because for each node we've stored the function that computed it and the value that was computed, we can apply the chain rule to that node, and because we stored the parents, we can propagate the derivatives back through the network. This sequence of intermediate objects with a value, parents, and a function can be stored in a list or other data structure, and this collection of objects storing the reverse mode automatic differentiation objects is referred to as a gradient tape. All of this can still be done if we have more complicated intermediate functions, as long as we know how to compute the derivative of those functions. And the value of these variables need not be a scalar, but can be a vector, matrix, or tensor. And so, as long as all of the smallest components of which our function is composed are differentiable, we can break that down with automatic differentiation and compute the partial derivatives of that function.